Let's get started, and for those of you who don't know me, my name is Javed Iqbal. I am assistant professor in nutrient management and water quality at UNL in Lincoln. So this is the site that I have been managing with my research team. I have one research student, Ashdeep Singh, and who collects data from here. Today he's not here because he has got COVID. So he's staying off for a few days. And then I have research technologists, two research technologists. Those are also collecting data here. So it is second year that we are collecting data from this site. This is the continuous con. This is the con the third year. But for our data collection, this is the second year. This site, we have been working with Carpenter's family. It has been really great to work with them. Really appreciate their help and the coordination to collect data from this site. We are mainly at this site, we are working on nitrogen management. And nitrogen management, we know that is the hard issue these days. How do we manage nitrogen more efficiently? And so at this site, we have got three kind of studies. So this is on-farm research trial, demonstration trial. We have three kind of studies at this site. One is the first study, we are looking at different nitrogen recommendations, different models, the models from the university and the models from the industry, and see how do they perform to improve nitrogen management, crop yield, crop growth, and water quality. How that can help us improve nitrogen management to optimize inputs and get the maximum returns. So that's the one study that we are doing at this site. The other study that we have at this site is testing next generation nitrogen fertilizers. So we are testing different nitrogen inhibitors with different timing of nitrogen application to see what is the best time to apply nitrogen with the next generation fertilizers, because those are the kind of nitrogen fertilizer those are more stable and can stay in the soil for longer period of time, right? So the question comes, when you want to apply, at what time you want to apply, how they are going to help you to improve the nitrogen management, to reduce nitrate leaching, to improve water quality, to get the maximum yield. So that's kind of second study. The third study that we have here at this field, looking at irrigation rates and nitrogen rates. So we are looking to see their main effect of nitrogen rates, low, medium and high, and irrigation rates, low, medium and high, and their interaction to see how we can optimize to get the best nitrogen rate with the best irrigation rate, to see how we can optimize those to improve nitrogen use efficiency and protect our water quality, and at the same time improve nitrogen use efficiency and get the maximum returns. So these are three kind of studies that we have got at this site, and this is the first kind of on-farm research trial that I know of where we are collecting intensive data. We are collecting a lot of data, and my research team from Lincoln, they come here 2 or 3 times every day. So they are spending 16 hours a day and collecting as much data as we can about nitrate leaching so that it can help us to make some decisions. So I cannot go through all those 3 studies today, but we will go through one study and kind of give you an overview what we are doing and how we are doing and what we are seeing here. So I have these handouts. If you can all get these handouts. So these are the handouts from one of our study where we are testing nitrogen rate from different nitrogen models. We know again the nitrogen rate, right? That's our biggest challenge. We always talk about nitrogen rate, but sometimes forget about nitrogen sources, place, right? The nitrogen source, nitrogen management is a really challenging, especially it can not only affect your farm, it can affect the surrounding environment, and how it protects, how it how it affects water quality and the whole community, because nitrogen is really a volatile compound. Among all the nutrients, nitrogen is one nutrient that can be easily lost from the soil into our surrounding environment. It can be lost through groundwater, through nitrate leaching to groundwater, or it can lost through gas into the air. So the question is, how do you manage nitrogen, right? With this so many volatility, how it moves. At the same time, the farmers have to make decision how much nitrogen is the right rate every year. Every year is different, depending on weather conditions, how much rain you are getting, how is the soil temperature, how are the other conditions. You may not have the same nitrogen rate every year. You have to decide how much nitrogen you are going to put. So my question here is, I just want to know the group. How many of you are crop consultant? Okay. How many of you are directly farming? Okay, so one. Okay, say again.
I'm farming, is that what you asked?
Yes, right. Oh, good to know. So my question is, how do you decide how much nitrogen do you want to put to your crop, to your corn every year? How do you decide that?
We use 1.2 times the yield.
1.2 times the yield. Okay. Any other?
University algorithm.
University algorithm. Okay. All right. So there are different ways to know how much nitrogen you want to put. But the question is, the nitrogen that you are putting, is that the most economical optimum nitrogen rate? Are you getting the most return from that nitrogen rate that you are applying, right? So this is the question, and then there have been different theories involved in making this decision how much nitrogen you want to put. For example, 1.2 for each bushel of yield, right? That's one way, and then the other, different people are thinking differently. But there are some nitrogen models, nitrogen recommendation tools that can help to make this decision easier. How much nitrogen you want to put, that is the most economical nitrogen rate. You don't want to put too much nitrogen that you are losing nitrogen, you are losing profit. You don't want to put too less of nitrogen that you are losing yield, you are not getting the maximum profit. You want to pick a rate that we call economic optimum nitrogen rate, EONR, that you would see here. So this rate is the rate where the last increment of nitrogen gives you large enough return for the yield that it pays off for that last increment, right? That is economic optimum nitrogen rate. But the question is how we find that out. There are different models, different tools that can help you to decide what is the EONR, where this rate is. For example, there are university-based tools, UNL nitrogen calculator or algorithm, Mason. Those are two tools from the university, UNL. And then there is another tool, sensor-based fertigation, crop canopy sensor. Different terms are used for that. These are the university tools. There are some tools that those are introduced by the industry. For example, Adaptan is being introduced. Granular N is another tool. But which tool is the best? Every tool can give you the different nitrogen rates. But how do we know which tool is the best? Some tools are free, some tools you have to pay off, right? So in this study, we were looking to test those nitrogen tools to see which nitrogen tool can give us the best yield return, net return, but also protects our water quality. So in this study, we have used those 5 tools, but at the same time, we have also determined economic optimum nitrogen rate on our own. You cannot do that, at every field. In order to do that, you have to have different nitrogen rates at your site so that you can calculate yield response curve to that nitrogen rates, and then from that yield response curve you can know your true economic optimum nitrogen rate. Okay, so in order to do that, if you will look at the table 1 on page 3, the treatment which is called N-ramp. So the first column, N-ramp treatment, in that the next two shows different nitrogen, 6 nitrogen recommendation, nitrogen rate, what we thought is our recommended and what we applied. So from these 6 nitrogen rates, and then all of the nitrogen rates that nitrogen that I'm going to share here, they are combination of like pre-plant, side dress, and 3 times fertigation. Okay, all of those rates. All right, so we applied at every 60 pounds from 14 pounds nitrogen to 314 pounds nitrogen. So we were able to to calculate economic optimum nitrogen rate for this site. Last year, the data that I'm going to share is the data from the last year. So what we found, what we calculated, 230 pounds nitrogen was the economic optimum nitrogen rate from this site. I will talk more about that in the next tables. And then, so as I said, remember that 230 pounds nitrogen was economic optimum nitrogen rate. And then, so when you are, when you want to calculate economic optimum nitrogen rate, there is not a fixed number. There is a randomization. There is a range that we calculated from the randomization of our plots, and that range was plus minus 15 pounds of nitrogen. Okay, so that would range from 215 to 245 pounds nitrogen. If you are within that range, you should be the most happy farmer, that you are lying in that range to get the most economic optimum nitrogen rate for the economic returns. All right, now let's compare what the other models recommended. UNL nitrogen algorithm recommended 237 pounds, so it was within that range. Mason, it recommended 253 pounds. It was outside of that range. Okay, so now when I'm saying these, rates from these tools, these are the nitrogen that we are putting into the soil after taking nitrogen credits from soil, from any previous crop, from irrigation credits, etc. Okay. And then sensor-based fertigation, it recommended 171 pounds nitrogen. But we were only able to apply 164 pound nitrogen for sensor-based fertigation because we had 3 fertigation, we were not able to apply more than 30 pounds nitrogen with each fertigation. Adopt N, it recommended us 224 pounds nitrogen. So that was without taking nitrogen credits from irrigation. But that was also within economic optimum nitrogen rate. However, because they did not take into account nitrogen credits from irrigation, we did that on our part, and we reduced that rate. So we applied 11 to 12 inches of irrigation last year. So we took that nitrogen credits into account and reduced this rate from Adopt N to 164 pound nitrogen. Granular N, it recommended, by the way, the same rate, 224 pounds nitrogen. So it was within that range. Again, we took into account nitrogen credits from irrigation, reduced that rate to 164 pounds. All right, now let's look at the results and see how those models performed. If you go on the page 5, you will see that the first figure, it shows, okay, so corn grain yield. Now in this, there is a yield from 0 bushels to 280 bushels per acre on the y-axis. All right, so there are two gray areas. So one is vertical gray area that says EONR. So that indicates a range of EONR, 215 to 245 pounds nitrogen. Okay, the horizontal gray area indicates the corn grain yield that we got with that economic optimum nitrogen rate. So that is the range of corn grain yield. So now different dots from different symbols from different models you can see. First you can see the maize N. You can see it was above economic optimum nitrogen rate to the right, but its yield, corn grain yield, was within the range of yield at economic optimum nitrogen rate. So that means you are putting more nitrogen, but your yield is still within the economic nitrogen rate, but you are putting more nitrogen. Second, look at the UNL nitrogen algorithm. It was in that gray area at UNR and yield at UNR. So that indicated that UNL nitrogen algorithm was very close to the true economic optimum nitrogen rate. So its yield was close to, it was to about 260 pounds, 60 bushels per acre. And we got 259 bushels per acre from economic optimum nitrogen rate, average. The range was about 240 to 275. Okay, let's look at the adoptant and granular, those triangles. So you can see this, the rate is lower. It's on the lower, on the left side of UNR, but its yield is still within that economic yield at economic optimum nitrogen rate. So that we analyzed the data, we found that there was no difference in corn grain yield between all of these models. So there was, they were all within the economic optimum nitrogen rate, but some of them they are putting more nitrogen, some of them they are less nitrogen, right? So, and then sensor based fertigation. So one thing that I didn't mention earlier, so we had same nitrogen rate for adoptant, granular N, and sensor based fertigation. If you I will get you back to the table 3. If you look at the last three models, you can see sensor based fertigation is a kind of model where you would put some nitrogen as pre-plant, for example 60 pound nitrogen as pre-plant, and then you will not side dress nitrogen. At V8 stage you will come back and use a crop canopy sensor just like this rapid scan sensor, and then will detect, run this over your crop, will measure how much nitrogen you need to add to your crop. So you're not side dressing. So we did not side dress with sensor based fertigation, but we still we put 60 pounds as pre-plant and 30 pound with irrigation with each fertigation. But for adoptant and granular N, we did side dress. However, we decreased the fertigation rate by 10 pound. So instead of 30 pound, we put 20 pound with each fertigation. So the difference between adoptant, granular N, and sensor based fertigation is sensor based fertigation did not receive any side dress. Okay, going back to figure 1, you will see sensor based fertigation has the lowest corn grain yield, though it has the same nitrogen rate as adoptant and granular N. So what was the reason that it has the lowest grain yield? At V4 there was no side dress. So if there is no side dress, there is going to be a penalty in yield. You are going to see less yield. So there was 204 bushels per acre. So you are really seeing 50 to 60 bushels less yield with sensor based fertigation. But that doesn't mean that this tool is not performing. There are different ways to test this tool. This one, we use the Solari algorithm to test this tool where you are not side dressing. This works well where it is sill loam soil. It does not work where there is a sandy soil. That's what we were looking to test. Whether that algorithm that has been tested at silt clay loam soil and has been said that that performed well without side dress. But we were looking to see whether it performs here. No, it does not perform.
What is the algorithm?
It's Solari algorithm. S-O-L-A-R-I. Solari algorithm.
Who produced it? What is that?
This algorithm was produced at UNL.
Oh, okay.
Yes.
With,
It was with rapid scan sensor. But now there is another Hewlett-Shepard algorithm as well. So there are two algorithms. Okay, but with different timing of nitrogen application, what I am talking about.
okay.
Even you can use Solari algorithm in another way. Okay, for example, you can side dress nitrogen. You can apply nitrogen as pre-planned, side dress nitrogen, and then come back before you decide on fertigation and still run this sensor to see if you need to apply more nitrogen. So I think that is a more kind of improved way that you can use to use this sensor. So, but we do not want to skip side dress, okay, because that's going to end in yield penalty. All right, now let's talk about the nitrate leaching that we found from these 5 models. If you see on the figure 2 on the same page, you can see the same nitrate leaching from EONR with vertical gray area, nitrate leaching at EONR range with horizontal gray area. You will see that maize N had the highest nitrate leaching, but its nitrate leaching was kind of similar, statistically similar to nitrate leaching at EONR. In magnitude, it has higher nitrate leaching. UNL nitrogen algorithm has the same amount of nitrate leaching that we had at EONR. Adopt N and granular N, they had about 40% lower nitrate leaching compared to EONR. So you can see that on the right, on the left graph, the yield from these two models, it was within that range, right? But it reduces nitrate leaching dramatically. So it reduced nitrate leaching by 40%. Sensor-based fertigation, it also reduced nitrate leaching by 45%. So that shows that reducing nitrogen rate by 50 to 60 pound can reduce nitrate leaching by about 40%. But now the question comes, that the farmers would be most interested. What rate is economic? We definitely want to reduce nitrate leaching, right? But what is our rate like that we want to use without losing any net returns? So if you see on the last page, table 6, we have nitrogen rate again from each of those. We have nitrogen rate that we had from UNR to 230 pounds nitrogen per acre, and the nitrogen rates from other models. We have got corn grain yield from each of those. And then at the end we calculated marginal net return from all of those models based on the price of the corn and price of the fertilizer. And these prices are for last year. This is not this year. This year prices are very different, right? This data is from last year. All right, so now you can see the letters on the last column, the letters A indicate that there was no differences in net profit, between those numbers which has got the letter A. The letter B, which is from crop canopy sensor, was statistically lower, has a less return compared to all other models. Now the question is, you probably would be more interested in looking at the numbers now rather than the statistical differences. You will see, all right, maize is giving us, $18 more than UNR, and UNL is giving less, a few less, and then adopt N and granular N, right? Though there are not, there are some differences magnitude wise, but the question is, as you have seen, and they're all in that range, right? Some of them, they are on the upper side of that range, some of they are on the lower side of the range. But the question is where you want to be. Do you want to be on the upper side of the range and reduce and have more nitrate leaching, or do you want to be on the lower side of the that range and decrease nitrate leaching but still be in that economic optimum nitrogen rate range, right? So that indicates that yes, maybe if you can lower nitrogen rate to the lower end of that economic optimum nitrogen rate, you can still, or even lower, as you can see in adopt N and granular N, you can decrease nitrogen rate dramatically but still be in that economic optimum nitrogen range and still reduce nitrate leaching by 40%. Okay, so it's a kind of win-win situation. But again, okay, so these are the marginal net return that you would see based on the prices of corn and prices of the fertilizer. We have not yet added the prices of nitrate contamination, the cost of remediation of nitrate from the groundwater. If you will add those costs, and we are working on that to figure out that, and we want to add those costs in these parameters and then calculate net return based on the cost of cleaning the groundwater. That means probably you will see more returns on the lower end of economic optimum nitrogen rate, and that's for the that's a net economic return for the whole society, and that's where we want to be, right? So overall, this was 1 year data from where we have seen that if you are going to reduce nitrogen by 40 to 50 pounds, you are on the lowest range, or even little lower range than UNR, but for your net return you are still within that range. It can be lower end of that range, but you are still within that range, and that is good for the society. And so this is again 1 year data. We are collecting 2nd year data this year, and we'll be sharing that data sometime during the winter or next year whenever we see the opportunity. So another study that we have inhibitors, in that study we have also found that if you would decrease nitrate leaching, decrease nitrogen rate with inhibitors by 40 pounds, you will see the same yield that you are getting with EUNR. So it was 260 60 bushels per acre with putting 40 pounds less with inhibitor. But that is the data that will come sometime, and we would like to share. Now I will just like to go over little activity, and will take you to the field to share with you what we are doing, and we'll do a little exercise till we have time. But I want to hear, before we go there, I want to share with you what we are doing, how we are collecting data. We are collecting a lot of data for a lot of water samples from all of these plots. So we have installed this suction cup lysimeter. These are 5-foot lysimeter that you can install at some depth below root zone, right? So we have installed this suction cup lysimeter at 4 feet depth. So this part is above the ground and this part is below the ground. So what do we do? Then we have installed these at the start of the season, and then we are leaving it there, but every week 2 or 3 times we are coming, and we are using this vacuum pump to apply suction through these tubes in this suction cup lysimeter. So it creates suction, and then the water around this starts to get into this tube. And then after a few hours on the same day, after a few hours we will just like collect the water from this tube through this syringe, and then we'll take this water with us and analyze that to determine nitrogen.
How deep is it?
So it is 5 feet. We have installed at 4 feet. We have left 1 feet above the surface, and 4 feet we have installed it there. And then there are different length. We also have this short lysimeter. This is a 3 feet lysimeter as well. But we are using here at this study, we are using this suction cup lysimeter, long suction cup lysimeter.
What have you found so far?
What we have found?
Nitrate, yeah, where are the nitrate levels at? Are they
Okay, so nitrate levels at 4 feet depth, you can, like nitrate level, they are above 30 parts per million. Okay, but it depends on the time. When you are right after fertilizer, there are higher levels of nitrate, and then at the end of the season there will be lower level of nitrate. Okay, but we are just collecting water sample, few water sample to measure nitrate nitrogen in those, but we don't know how much water is flowing through the ground, right? So once we know the nitrate concentration in the water, we can calculate how much nitrogen was, how much nitrate concentration was in that water, how much nitrogen, how much water drained through the profile. In order to know that how much water drained through the profile, we have installed these moisture sensors at different depth. So this is just an example. We have installed these moisture sensors at 4 depth, 1 feet, 2 feet, 3 feet and 4 feet depth. So we can see the change in moisture conditions every day. And then we already know how much irrigation we are applying, we already know how much rain we are getting, so that using these numbers we can calculate how much water is flowing. And then at the end of the season, we will be able to calculate how much pounds nitrogen per acre we are losing in the soil. So we are using these moisture sensors with this watermark monitor through which we can download the data for the moisture sensors. And then we are also testing different ways of analyzing nitrate leaching, right? This is one way, that is well known way of collecting water sample to analyze those samples. But we are trying some new methods to see if, rather than coming here 3 times a week, can we do something that we can try a new method where we can just put something into the ground and come after a couple of months to collect that sample, what we call resin, ion exchange resin, that we are we don't I don't have it here, but we attach those resins at the bottom. We dig in the soil and then put this tube into the soil, and every month we are coming back to to replace the ion exchange resin, and then we collect that ion exchange resin to analyze for nitrate concentration. So this is a new method that we are trying here. I will show you in the field. All right, now little activity that we have got. We know there are a lot of nitrogen tools to determine in-season nitrogen application, right? Some tools you don't have to come into the field, like Adopt and Granular will just recommend you based on the weather conditions and some data you will provide. But some cases you really want to know how much nitrogen you want to put, just like crop canopy sensor, right? So that is a tool where you can come into the field and see the condition of your crop and decide how much nitrogen does your crop need. Okay, so for this I picked the wrong one. Okay. All right, so for this we are using a crop canopy sensor. There are different kinds of sensors. This is a rapid scan sensor from Holland Scientific. Okay, so which you can scan over your crop. It will so once you will run this over the crop, light from this center sensor would be modulated on the crop canopy. So once it is modulated on the crop canopy, the light from the crop canopy is reflected back to the sensor, which is detected by the sensor, and it gives you a kind of number from the wavelength that is measured. That number, what we call vegetation index. There are two types of index, NDVI and NDRE. So here this can measure both, but I am showing here the NDRE. So this sensor will give you the NDRE reading. Now the NDRE reading that you have, you need to collect from two crops. One is the target area where your farm is, where you want to see how much nitrogen you need to apply to your crop. Okay, so that's a big area. That is more kind of deficient area where crop may need nitrogen. But you may also want a small area of your farm where the nitrogen is non-limiting. So you may apply few more pounds nitrogen just in that area so that it is greener, and then it can give you a kind of reference how much nitrogen you need to apply to your target area. So what you would do, you will run this crop canopy sensor in both areas. For example, here the NDRE values from target area is 0.319, but from reference area it is higher, 0.38. That indicates that has sufficient amount of nitrogen, but this area needs nitrogen. So you can calculate a sufficiency index from those both NDRE values. As you can see, target area NDRE divided by reference NDRE. So you can calculate sufficiency index that will give you a kind of index that you can use in this algorithm, Solari algorithm, to calculate in-season nitrogen rate that you need to apply to your crop. Okay. Now today we have got these two areas here, and I want you to do this exercise and then run this rapid scan sensor in those two areas, and use this formula to calculate how much nitrogen does the target area needs. Okay, so